Simultaneous equations are one of the most powerful tools available to a mathematician. Up to now, you've probably just been taught how to solve them if you're given them, and you may have been taught a tiny bit of modelling to create simultaneous equations. But before we go on to talk about how we can solve linear and quadratic simultaneous equations, it bears to take some time to go into it in slightly more detail. When we talk about solving simultaneous equations, what we're actually saying is that we're going to solve a system of equations simultaneously. And by simultaneously, we mean where do those systems of equations have the same values or the same solutions? And the key in this process is the system itself. So what is a system? A system is a context described using entities and processes. Okay, so as an example, we can take a real-life scenario and model it into a system in which we abstract certain entities and processes and then describe them using the beautiful language of algebra. So let's consider an example. So say we have two cars and they're setting off from the same point but at different times, and we want to know at what time they'll meet. Okay, so it's a bit of a contrived example, but most of these are at a basic level. So our system would be described by using a graph, and some of the descriptions we'd use, or the descriptors, would be time and distance. Okay, so we have time and distance here, and then we could say, okay, we're all starting from the same point, so car 1 would have an equation that drives this way, so that'd be car 1 described by a straight line. And then car 2 might set off slightly later, but it might be slightly going faster, which would be shown by a steeper line. That's car 2. Okay, so this is our system already. We've described two cars driving around in relation to the distance from a certain point to the same point and the time that they took from the time car 1 starts. Now, this should be where it's obvious what simultaneous means. Where do both of those equations which describe the two cars exist simultaneously? Well, they only exist one place simultaneously, here, okay, at that intersection. And solving simultaneous equations is essentially solving systems of equations to find out where they have the same solutions or where they intersect. So this is the intersection, where they have the same solutions that exist simultaneously. And that's all simultaneous equations are. And this is a very simple system, but as you can imagine, they can become quite complicated because obviously you may need to have more variables. We've got distance and time here, and you may have more than one equation. In fact, there's a whole branch of mathematics called linear programming that deals with this, that's used in business and industry. Now, this is an example of two linear equations, and you should be able to see that because car 1 is defined as a linear equation, a straight line, and car 2 is defined as a linear equation. But in reality, when we look at the real world and we try to model, we can model behaviours of entities using lots of different equations. And that's where this idea of solving different types of equations comes together. So as an example, we may end up having something similar here. Oops, wrong colour. So say we've got a different system where we're throwing a ball. So again, we've got height here, and say we've got time here. Now we could say that starting at 0 time, the ball is at 0 height, okay? And again, that's an implication of a model. So let's not say that. Let's say a person's throwing it and they're 2 meters high, okay? So they're throwing it from 2 meters. They throw a ball. Now, you know from practice and experience, if you throw a ball, it will follow some sort of parabola like that. Okay, so there's the equation 1, which is the trajectory of a ball, and then it'll hit the ground, and yes, it'll go boing, boing, boing. But we don't consider that, okay? Because one of the beauties of modelling is that we only consider bits that we consider to be accurate or relevant to the problem we're trying to solve. Now, a second equation could be a person running to jump, okay? Now, they may run and jump following a different equation, and their running and jumping could be, for instance, this equation, okay? Person jumping, okay? Now, if we were to say, well, is the person going to catch the ball? Well, let's see. We follow the flight of the ball. Here we go. Oops, a daisy. No, we don't. How do we follow the flight of the ball? Okay, and we see the flight of the ball goes along. And then we see that the person jumping goes. And so what we're looking for is where they meet. Do they meet? Yes. So we could therefore say we know the person's going to catch the ball at this time, and we know that they will catch the ball at this height. Okay, H1. So again, that's the power of simultaneous equations. But what you'll notice in the second one is we have different types of graphs. So in the first one, we had two linear equations, straight lines. But here we have a linear equation, the person jumping, and a linear equation to describe the ball. Now, hopefully some of you might recognize that sort of looks a bit like an inverted or negative quadratic. And that's where, if we were going to solve these algebraically, we'd be solving a linear and a quadratic simultaneous equation. So, although I could just show you how to do them, I think it's much more important you understand what you're trying to do first, because then manipulating them makes much more sense to you. So the general rule is, when we're creating our system, we have a set of variables or unknowns that change. And for each variable, we need one equation. So as you know, you've been solving linears and linears. That's an x and a y usually, and that gives you two variables, so you always need two equations to solve it. Okay, there are many different types. You can have 3s, 4s, 5s, all sorts of things that go on. They become slightly more complicated, but only in terms of process and how much work you have to do. But ultimately, they're all solved in the same way. But what's key here, I think, is understanding the visual context. If you can see in your head what you're trying to do, it makes working these out much easier, and also it gives you the ability to understand whether your answer makes sense or not, because you can reinterpret your answer in terms of the system and the model you've created. So let's apply our idea of visualizing simultaneous equations to what we already know, linears and linears. So in a linear and a linear system of equations, we have two variables, which are x and y, and that requires two equations involving x and y to be able to solve them. Okay. Now, when we say two variables, you're probably looking at this and going, well, linear 1 is defined as y equals x plus b. Linear 2 is defined as y equals ax plus b. There's 1, 2, 3, 4 letters there. But remember, the a and the b are just coefficients. They're constants or numbers, okay? So they're not variables. They don't change. What changes, and that's what we're talking about when we mean variables, something that changes, are the y's and the x's. Okay, so this is two variables that are going to change, x and y, and that requires us two equations. They're in this form, y equals x plus b, which is just a more generalized version of what you know as y equals mx plus c. Okay, so if we're thinking about this, how many ways can we're trying to solve these simultaneously, how many possible interactions can there be? Okay, so let's have a think about this. So we have an x and a y-axis because they define our variables, our unknowns. And we have two lines. Now, the lines, no matter how you draw them, what we're trying to do is work out how many ways they can possibly interact. So no matter how many ways you draw two lines, okay, whether you draw them that way, or whether you draw them x, y, whether you draw them coming down or coming across, they will only intersect at one point. Okay, so what we do know is that linear and linear, if you're trying to solve them simultaneously, one interaction is they intersect at one point. Can they intersect at more than one point? No matter how you move those lines around, they can't. But what about 0 points? Okay, because we need to understand as mathematicians the complete system. So we've already said, well, they can definitely interact by intersecting at one point. We don't believe they can interact by intersecting at more than one point. But what about 0 points? Let's have a look. So if they never interacted, what would that mean? So here's the equation of, say, here's the first line. The only way lines can't interact or intersect is if they are parallel. And that is a valid context within this equation, isn't it? A very valid instance. So we know then that we can have, for linear and linear, we could possibly have 0 solutions, okay, where they don't intersect, or we could have 1 solution, which is where they do intersect, okay? Now this is important because as we move forward and start using different types of equations, quadratics, ellipsoids, reciprocals, trigonometric graphs of sine and cos and tan, the way those equations interact with each other will define the potential number of solutions that we can get. Okay, so we've looked at linear and linear. Hopefully that makes you see what we're trying to do. And now we'll go and look at linear and quadratic. So let's look at the next ones, linear and quadratics. So linear equations have the form y equals ax plus b, which is the same as y equals mx plus c, just different letters. And the quadratic has the form y equals ax squared plus bx plus c. Now, if we think about the graphs, that's what we want to think about visually to decide how many solutions there are going to be. So we know a line's a line, so we'll draw that in later. So let's see. So here's some basic axes. So what could we have? Well, we could have a positive quadratic. Okay, so positive quadratics are of the form a is greater than 0. All right, and these are sometimes called smiley faces, okay, because they look like smiley faces. They are parabolas is the posh word. So there's our quadratic and we have a line. So a line could intersect at 2 places. Yeah. What else could it do? Well, it could also intersect at, or not intersect, but touch, so that it exists at the same time, the same space, at 1 place. So it could be like that. Which another word for that would be a tangent, because it touches the curve at 1 place without going inside it. Okay, and the final solution, if you can think about it, what's the final scenario we could have? Well, we can have our quadratic, and we can have our line that never goes through it. Okay, never intersects it. So we can possibly have 2 solutions, 1 solution, or 0 solutions. Okay, so 0 solutions where it doesn't cut it, 1 solution, a tangent, and 2 solutions. This is a posh name for this is called a secant. Okay, so this is a tangent, and this is a secant. Okay, now there are 3 solutions for when a is greater than 0. So what about when a is less than 0? Well, when a is less than 0, we have something similar. So let's consider, if a is less than 0, what shape do we have? For the quadratic, we have a sad face, okay, or an inverted parabola. And again, we will have the same sort of things, except this time it will be upside down. So there's your inverted parabola. So we can have our line cutting at 2 places. So there they are with our secant. We could have our tangent version where it cuts, or doesn't cut it, it touches it at 1 place. Or we could have our, let's draw over there, we could have it where it doesn't go anywhere near it. Okay, so that could be, for instance, like that. Okay, and that would give us our 2 solutions, or 1 solution, or 0 solutions. So when you're working out linear and quadratic equations, be aware, and simultaneously you could end up with 0 solutions, 1 solution, or 2 solutions. And if you think about the graph, this is why. Now, if you're trying these and practicing them at home, or anywhere near a computer or a tablet, you can use Desmos, desmos.com, or GeoGebra.org, type in the equations, and it will draw them for you. Now, sometimes you'll be asked to draw them in a question, in which case what you're going to do is work out an estimate for the solutions, okay? Because obviously whenever you're drawing off a graph, everyone's graph is slightly different, so you can only ever estimate. But if you have to work them out exactly, or you have to work them out using algebra, then you're going to be solving essentially a quadratic equation. So that's linears and quadratics. Now, before we get any further, we'll have a look at a few other ones, just so in your mind you understand what we're trying to do here, the nature of what a simultaneous equation system is. Okay, and we're going to look at some other types of graphs. So here's another example you could end up with. You could end up with a linear and an ellipsoid. Now an ellipsoid is basically a posh name for the family of convergent parabolas, or better known as circles if they're symmetrical, or ellipses if they are not. Okay, and you can tell them because you've got a square on both the x and the y value. The r, as you should hopefully know, is the radius, so r squared is usually a number, a constant, okay? But it's the x squared and the y squared you're looking for. Now, if you think about it, instead of drawing the divergent parabola, which is what we get from quadratic, we've got a convergent parabola. So where the two ends go, instead of diverging away from each other, they come together and they join, okay? So let's think about that. Let's consider a straight line and a circle as an example. So what's visualizations can we see for intersections between a straight line and a circle? So let's see, there's our grid. So a circle, there's a circle. So we can have a line cutting through at 2 points. That gives us our secant solution, doesn't it? So there and there. So that gives us two solutions for a secant. Oops, secant. Or we could have a single solution where we have our circle and a, if it joined it, oh, that's terrible. It's not a straight line, but you know what I mean. So there's one solution. So that's our tangent to the circle. Okay, or we could have it missing completely, which would be terrible if it missed completely, but again, so let's say there's a circle. Oops, gosh, there's a circle this time, and our line could be completely failing to cut it, so we'd have 0 solutions. Okay, and again, they are for circles, which would be x squared plus y squared equals r squared. If we have coefficients in front of them, the a's and the b's greater than 1, or they're less than 1, we can have as well, we would get an ellipse. And you can try this out on Desmos or GeoGebra, but you may have something that looks like this as an ellipse. See how badly my ellipses are? It could be something that looks like a squashy egg thing. But again, there's only 3 ways we can see a line working with this ellipse. It's either going to cut straight through it as a secant for our 2 solutions, or it's going to touch it at just 1 point, which is our tangent, isn't it? So there we go, whoopsie-daisy. So it could be going there, there's our tangent, or it could miss it completely. Okay, in which case, let's try the long one this time. Whee! Okay, or it could miss it completely, it could go that way, for instance. Okay, but there we are. So thinking about linears and quadratics, linears and ellipses, you could end up with 0, 1, or 2 solutions based upon the nature of the interaction. Here's our first example then, and there are many types of examples of linear and quadratic simultaneous equations, and a lot of them need rearranging to start with, but ultimately the first thing we need to do is work out what sort of equations they are. So quick look at these and we can see that the first one has an x squared, so it is a power 2, there is no x, there's a constant, so this is a quadratic expression, a quadratic equation, so that's quadratic. One below it, well, it's in the form y equals mx plus c, isn't it, already? So we know that's a linear, so this one's nice and easy. So, given that we know the types of equations now, we know a quadratic and linear could have 0, 1, or 2 solutions, which we talked about earlier. Now, to solve simultaneous equations, the method we've used so far, the linear and linear, is equalization. So in that, we try and set one side of the equations to be the same, and if one side is the same, the other side must be the same. In this case, the left-hand side, the LHS, is already the same. So that's equalized, which means we can equalize the right-hand side. So this is a nice and easy one, okay? We don't need to complicate this. So we know that if y and y are on the left-hand side and they equal each other, the right-hand sides must equal each other. So we can write that. That's eliminated a y out of our simultaneous equations. We've only got one variable, the x, so we can solve it. So x squared minus 5 equals 2x minus 2. We can see that's going to be a quadratic equation as a power 1x, power 2x, and a constant. So if we rearrange this and we let them equal 0, because that's how you solve quadratic equations, we set it so that it equals 0. So here we go. We say x squared, bring the 2x across, so it becomes negative x. Bring the negative 2 across, becomes positive 2, so that becomes negative 3 equals 0. First thing you want to do, can you factorize it? Okay, if you can't factorize it after 10 seconds or so, use the formula or complete the square method. In this case, we can though. We know that's x and x. We know that's 1 and 3. That's how you get the 3. The 3 is negative, so the signs are going to be different. And the coefficient for the x term is negative, so that means the biggest number must be negative. So that's got to be a minus, which means that's got to be a plus. So in that situation, we multiply out just to check. So x times x is x squared. X times minus 3 is minus 3x, plus 1x is negative 2x, which is there, and plus 1 times negative 3 is negative 3. So we know how it works. So now we solve each of these brackets by letting the bracket come to 0. So for this bracket to be 0, it's x plus 1 equals 0, so x must equal negative 1. And for this bracket, x minus 3 equals 0, so x must equal positive 3. All right, now we're looking for intersections, right? So this is on a Cartesian grid, which is two-dimensional, because we've got x and y axes. So it's not good enough just to come up with the x's, we need the y's as well, which we get by substituting back into one of the equations. And obviously, if you can help, you want the simplest one, which is virtually always the linear. So if we substitute back into the linear for x is negative 1, we get y equals 2, negative 1, take away 2. So y equals negative 2, take away 2. So y equals negative 4. Okay. Now, make sure you write that as the solution, the coordinate pair, okay? Because you can lose marks in an exam if you don't associate them with the correct one. So negative 1 comma negative 4 is there. And for the x is plus 3, we've got y equals 2 plus 3 minus 2. So y equals 6, take away 2. So y equals 4. So we've got 3 comma 4. And they are our two solutions. That tells us this linear is going to cut through this parabola at 2 points, so it's a secant to the parabola. And if we go on to Desmos and check, we'll see that is in fact the case. So here we can see y equals x squared minus 5 as the red parabola, okay? So we should be able to know, if we know our transformation of graphs, that minus 5 outside of the function affects the output, so it drops it down in the y-axis. So this is y equals x squared that's been translated by negative 5, which is why it's cutting through the y-axis at negative 5. And the linear, well, it's in the form y equals mx plus c. We can see that the gradient is 2, so we can see that for every 1 we go along, we go up 2, and then we can see its c is negative 2, so it should be cutting through the y-axis at negative 2, which it does. And it gives us our two solutions if we were going to graph it. So we can see our two solutions are one's there and one's there. And algebraically, have we got them right? So we worked out we had negative 1, negative 4, negative 1, negative 4, and 3, 4 is up there. Okay, so there you go. We've used Desmos visually to show us that we were correct algebraically. Here's our second example. So first step, what sort of equations are they? And we should be able to recognize that the top one is of the form x squared plus y squared equals r squared. Okay, where r is the radius. So this is some sort of ellipsoid, and this one, because the coefficients of x squared and y squared are 1, is a circle. All right, so we know that this is a circle. And we know the bottom one is a linear because we've only got power 1s in it. Okay, so that's going to be linear. And we know from our visualization we did earlier that a line and a circle can interact in 0 ways, 1 way, or 2 ways. So next step, can we equalize? Now, whilst equalization is a really easy method and works for a lot of things, sometimes it won't work. So although it will work here, I'm going to start to show you a second way of solving simultaneous equations called substitution. Okay, so I'm going to show you how they both will work, because in this situation they will, and then we'll move on to one where you can't use equalization. So let's have a go. So we'll use equalization on this side. Okay, so let's equalization. So to equalize, remember, we need one side to be exactly the same with one variable, and we need the other side to just have the other variable on it if we're doing a system of two variables. So we'll start off like this, x plus y equals 6. So top, the variables are squared, bottom, they're not. So we can quite easily sort this out. Okay, so first thing, we can say x squared equals 20 minus y squared, and here we can say x equals 6 minus y. Now, we've got one variable on one side, one variable on the other side, but the x on the left-hand side isn't equalized, is it? So to do that, we need to square the x. Now, if we do that, and this is where we've got to be very careful, okay, we will square one side, x squared, but remember, we're squaring the other side, and this is where brackets are your friends. Okay, do not be tempted to think that if you square one side and get x squared and square the other side, you get 36 minus y squared. You don't even get 36 plus y squared. You're squaring everything, which means you're squaring a bracket, which means you've got two brackets that are going to multiply out. So far from getting 36 minus or plus y squared, you're going to get, yes, you'll get your 36, but then you'll get minus 6y minus 6y, which is minus 12y, and plus y squared. Okay, so now we have two equations where the left-hand side is the same. So now we can equalize. So now 20 minus y squared equals 36 minus 12y plus y squared. Okay, now this one is really, really easy, as you can see, because it's a quadratic. It's y's rather than x's, but it doesn't matter which letter we're going to work out first. So we need it to equal 0, so let's rearrange it. So first step, we'll end up with 2y squared minus 12y plus 16 equals 0. So that's our first level quadratic equation. Now we could try and solve that by factorizing, but before we ever solve a quadratic, if it's an equation, can we take a common factor out and divide to make it simpler? Well, yes, because in this, all three coefficients, 2, 12, or negative 12 and positive 16, are even. So we can take a factor of 2 out. So we could go to y squared minus 6y plus 8 equals 0. Divide by 2, which gives you y squared minus 6y plus 8 equals 0. And now this is much easier. Can you factorize first? Well, let's have a look. Yep, you definitely can. If you couldn't, you'd have to use the formula or complete the square. Okay, so we know that's y. We know that's y. Positive 8, well, what factors we have? 1 and 8 and 4 and 2. 1 and 8 won't get you to 6, but 4 and 2 will. Okay, there's 2 and 4. It's positive 8, so the signs must be the same, but it's negative 6, so the signs must be negative. Okay, so therefore the solutions to this for the y variable are y equals 2, y equals 4. Remember, the solutions are what value of y makes the bracket equal to 0. And then we're going to now need the x value for these y values. So we use substitution into one of the equations. Always use the easy one, the linear one. It's virtually always the easy one. And so we put x plus 2 equals, x plus 2 equals 6. So x must be 4, or x plus 4 must equal 6. So x must equal 2. And then we've got to be careful, write down the pairs of solutions. So when x is 4, y was 2. And when x is 2, y is 4. Nice bit of symmetry there. And that's our answer. Okay, so I'll just lump for that one. Okay, now that's how to do the whole method using equalization. Now, substitution just starts off slightly differently, but ultimately will give you the same quadratic, and then it proceeds in the same way. So if we're going to use substitution method, okay, substitution method. So what we say here is, we have x squared plus y squared equals 20, and we have x plus y equals 6. So we always rearrange the linear so that it is a value that can be substituted into the quadratic, or in this case, the ellipsoid, okay? So you can often rearrange just for x, or you can rearrange just for y, and sometimes one of them is better than the other. For instance, you don't want to generate a fraction if you can help it. In this case, it doesn't matter because we'll get similar results. So this is how we go. X squared plus y squared equals 20. X plus y equals 6. It doesn't matter, so we're going to rearrange this so it says x equals 6 minus y. Now, substitution involves taking something we've created and substituting it into the other equation. So we now have x equals 6y. But up here, there's x. So all we do is where the x is, we create a bracket, write out the equation, but because we now have a different definition of x, we stick that in there, or substitute it in. 6 minus y is s squared. Multiply it all out, so we get 36 minus 12y plus y squared equals 20. We can see it's a quadratic, and if we rearrange it, 2y squared minus 12y plus 16 equals 0. And if you look over on this side where we did equalization, you can see that that is that. Okay, so that's the only difference. In equalization, we equalize one side so that we can equalize the other side. In substitution, you rearrange one side so you can substitute it into the other equation. Okay, or rearrange the simpler equation so you can substitute it into the other more complex equation. Okay, but at some point you'll ultimately get a quadratic, which is what you're going to have to solve. So sometimes one is easier than the other. Sometimes you can use both of them, and sometimes you can only use substitution rather than equalization for reasons that you'll see soon. Now, let's just check this again using Desmos. And here we have the circle, x squared plus y squared equals 20. Its radius is root 20 because x squared plus y squared equals r squared. So if r squared equals 20, r is root 20, which is just over 4. And as you can see, just over 4, a bit more over 4 than just over. And then x plus y is 6. If you rearrange that, it's going to cut through at 6, 0 and 0, 6, have a gradient of -1, isn't it? And there you have it. And as we can see, there are our two, oops, that's not good. There are our two intersections. There's one, there's the other. Is that right? Well, 4, 2 is there, and 2, 4 is there. Okay, so that's how we do that one. Here's another example where we can use equalization and substitution, but in this case, as you'll see, substitution is a better method than equalization. So first thing we talked about in our previous attempts is what sort of equations are they? Now, the bottom one, patently, is a linear. It's got an x power 1 and a y power 1. So we know it's a line, but what's the top one? Do we know anything about xy products? Well, we don't recognise it, but we're mathematicians, so we can rearrange until we do recognise it. So in this case, if we wanted to, we could rearrange this so it said y equals 24 over x. And y equals a over x, as we should all know, is a reciprocal graph. Okay, so it's a separated graph, two parts that are symmetrical usually. And so if we envisage that, we can see that it could cut it at two places, classic secant. It could miss it entirely, or it could tangent it as well. Okay, I don't think there's any other ways there it could do it, but you can experiment with that if you like. So just using our maths knowledge, rearranging it, we could see that something we didn't understand is something we do understand. It's just been changed into a different format. Now, let's look at equalization. So if we use equalization, okay, we have xy equals 24 and x equals y minus 2. So we need one side to be the same and have one variable on it, and the other side to have the other variable on it. So we've actually, in changing it to a reciprocal, done what we wanted anyway. Okay, so if we keep the x on the left-hand side, and we rearrange the top, so the x on the left-hand side, we end up with 24 over y. So now we have x and x on one side, so that means we can write y minus 2 equals 24 over y. And we've eliminated the x value. So all we've got to do now is rearrange and create our quadratic. So first thing we're going to do, multiply both sides by y. So we're going to have y minus 2 equals 24. Multiply out y squared minus 2y equals 24, and create our equals 0 quadratic. E minus 24 equals 0. Okay, and then what we're going to do is solve that in a minute. Now, if we didn't realize that this was a reciprocal, we could rearrange it, we could have used the substitution method. Okay, and the substitution method is very powerful, especially when they already give you a linear where you've got x equals or y equals. Okay, so in this case, we've already got x equals, so we're going to substitute any value of x with our x definition. So in the top, where we have xy equals 24, and we now have x equals y minus 2, we're going to substitute. So where this x is, we're going to put a bracket, y equals 24, and then we're going to drop our redefinition of x into here, y minus 2. And if you look, this is just this, isn't it? So that's how they both work. But you can see here, substitution is pretty an easier method than equalization. Not by much, but what do we care? So off we go here then. So we're going to try and do this. First thing, can we factorize it? Well, what's negative 24? 1 and 24, no. 2 and 12, no. 3 and 8, no. 6 and 4, possibly. 6 and 4s could get us to 2 if the signs are kind. So let's have a look. So y, 4 and 6. It's negative 24, so the sign's going to be different. It's negative 2, so the bigger number has to be negative. That's our suggestion. Does it work? Y squared, negative 6y plus 4y gives you negative 2y plus 4 times negative 6, negative 24. So it does work. So solving these for our y values, we get y equals negative 4 and y equals positive 6. Okay, and then we just got to substitute those into the linear. X equals y minus 2. So x equals y minus 2. So x equals negative 6. So our solution is there is negative 6 and negative 4. And here we have, what do we have here? X equals positive 6, take away 2. So that gives us positive 4. So here we have 4, 6. So another nice symmetry. So let's have a look. Are we right? Let's have a look at our Desmos. And here we have it. So the red is what we can see of the reciprocal, the y equals 24 over x. And here's our line from x equals y minus 2. Here's our two solutions. We can definitely see them. Are they the solutions that we ourselves have created? Well, there's negative 4, negative 6. Negative 6, negative 4, which is that one. And here is 4, 6, which is that one. So yeah, so we've used Desmos to prove that our algebra was correct. Here we go with another type of example. So the first one we can tell power 1x, power 1y, so that's definitely a linear, so we like that. We like our lines, nice and easy. And the second one, well, there's an x squared, So it could be a quadratic, but then there's an xy, which is a product. And we know when we've rearranged a product, we get a reciprocal. So this is a reciprocal. So from our visualization and from what we looked at the example before, we know that's 0, 1 or 2 solutions. Okay, so let's start then. So can we equalize? Well, we can easily get x equals 5 minus 2y, or for the linear. But if we rearranged it so y equals, we'd have y equals 5 minus x divided by 2, which is a fraction. So we don't really want a fraction if we can help it. So it looks like rearranging for x would be nice. But the problem we've got with the reciprocal is there's an x squared and there's a 3xy. Okay, so the xy product is going to be difficult to get round. So in this case, it would be very, very difficult to rearrange so that you had the same thing on one side. Okay, so we'll forget about equalization here. We're just going to look at substitution. Now, as you can see, we have x squared and x. So we've talked about already rearranging the x in the linear so that it's x equals 5 minus 2y. And then, guess what? We have an x there and an x there. So we can just substitute this in. So in this case, substitution is miles better, okay? In fact, you might not even be able to do equalization. I haven't bothered going through that yet. But why would we? Mathematicians always like the simple solutions. So we've got x squared plus 3xy equals 18. And we've got x equals 5 minus 2y. So wherever there's an x in the reciprocal, we're going to put a bracket. So 3 bracket y equals 18. And then we're going to drop our x into the bracket. Okay, so 5 minus 2y squared plus 3, 5 minus 2y, y equals 18. So there we go. We've now gone from having a reciprocal with x and y to just a nice equation that looks like it could be a quadratic with just y. So we've eliminated x. So now we just got to multiply everything out, okay? So we could just multiply everything out, but as we're nice, clever mathematicians, we could recognize, and this is just a technique, that both of those terms have 5 minus 2y in it. So we could say 5 minus 2y, take that out as a factor, which leaves 5 minus 2y as a factor there, plus 3y equals 18. So 5 minus 2y here. So 5 minus 2y plus 3y is 5 plus y. Isn't it? Well, hopefully equals 18, and that's much easier to multiply out and sort out, isn't it? So 5 times 5 is 25. 5 times plus y is plus 5y minus 10y. Negative 2y squared equals 18. All right, and then just tidy it up and get it set to equal to 0. So let's see. I'll do this longhand to show you simple ways to do it. Now, what we tend to do is you've got minus 2y squared here as this power 2 term. Now, you don't really want a negative, but we know if we could move it to the other side, but then we have to move everything to the other side and then reflect it. Or we can just times everything by -1, which toggles it. So let's tidy up first, okay? So we've got 25, we've got take away 18, if we bring that across, we've got plus 5y minus 10y minus 2y squared equals 0. So 25 take away 18 is 7, hopefully. Plus 5y minus 10y is minus 5y minus 2y squared equals 0. Times everything by -1 to toggle it, toggle the signs and rearrange it, and we end up with 2y squared plus 5y minus 7 equals 0. Okay, now, is there a common factor for the coefficients? Nope, there isn't, because 2, 5, and 7 don't have a common factor. So we can try and factorize it. Will that work? So let's see. If we try the AC method, because a is greater than 1 here, we've got AC equals 2 times -7 is -14. and we've got b equals 5. So can we get to 5 from negative 14? Well, 7 and 2 will get you to 5, won't it? Plus 7 minus 2, so it's negative 2 and plus 7 are the values. So remember, we use those values to split the power 1 term. So we end up with 2y squared negative 2y plus 7y. Take away 7 equals 0. Oops, so this is quite a long question. Factorise the first two terms. So 2y, y minus 1. So that's got to be a factor of the second pair. Oof, equal to 0. So what do you have to times minus 1 by to get minus 7? That's positive 7 plus 7y, negative 7. Both of those have got y minus 1 as a factor, which leaves 2y plus 7. Whoops-a-daisy. So yes, you can factorise it. Okay, and then solve it for the y values. So y equals plus 1, or y equals negative 7 over 2. So now we've got the y values, we're going to substitute it in. X plus 2y minus 5. So x plus 2y equals 5, did I say? I forgot what it was now. Equals 5. Equals 5. Yeah. So x plus 2 equals 5. So x equals 3. So our solution is 3, 1 for that one. And this one's going to be a bit more horrible because it's brackety. It's fractiony, I mean. So x plus 2 times negative 7 over 2 equals 5. So x, 2's cancel, so that leaves you with your negative 7 equals 5. So x equals positive 12, yeah. So that gives us the pair 12, negative 7 over 2. Okay, so they are what we think it is with algebra. Let's have a look at Desmos. And there's our little beauty. And as we can see, the line cuts through the top arm of the reciprocal at 3, 1 and 12, minus 7 over 2, or 3 over 5. So, nice. Now this one is an example of where you can still use equalization or you can use substitution, but it's going to be a bit horrendous. And the reason it's going to be a bit horrendous is because if you look at the linear, you can see that whether you make x equals or y equals, you're going to end up with a fraction. And when you end up with a fraction, it just means there's lots of numerators, denominators flying around, and you just have to be careful. So there's no difference in the method, you just have to be careful. So first off, let's look at the types of equations. So x squared plus y squared equals a number, so we know that's going to be a circle. Okay, so that's nice, and we know this one's going to be some sort of line, because it's y equals mx plus c, or power 1 for x and y. Okay, so we'll probably go for substitution here, although, as I said, equalization would work if you wanted to try it. So what's the easiest? And in this case, it doesn't really matter. Okay, sometimes you want to look at what you're putting it into. So because it's x squared and y squared at the top, okay, they're equal value, if you like. So you're really looking at what's the simplest with the rearranged linear. Now, if it was 3x squared plus y squared, then you'd try and do the y equals, because you wouldn't want to do x equals, square it, and then times it by 3, because you're doing another operation. So little things like that help you to make a more simple process. But in this case, it doesn't matter. So let's have a look. What should we do? We'll rearrange the x, I think. So we'll say 5x equals 21 plus 3y. So therefore we can say x equals 3y plus 21 divided by 5. I think that's right, isn't it? Y equals, so we're going to do it that way. Okay, hopefully that's right. 5x equals 21 plus 3y, 3 by 21, divided by 3. Yeah, I like the sound of that. Okay, so let's get down on boogie, shall we? So we have x squared plus y squared equals 45. And we've rearranged x, which means that we're going to substitute x. So we're wrong. So we're going to go bracket where there's an x squared plus y squared equals 45. Then in the bracket, we're going to put this thing, because this is now what x is. So we're going to put 3y plus 21 over 5. Okay, now this is where it gets horrible, because as you can see, you're going to have to square it. Okay, now there are lots of ways you can make this easy on yourself, and if you're lucky, you'll probably have a calculator to do this. But let's try and do the whole thing. So we have on the top 3y all squared is 9y squared. 3y times 21 is 63, and then it's doubled, so 63 plus 126y plus, oh god, what's 21 squared? 21 squared is something horrendous, I think. Hang on. 441 from the looks of it. 441 all over 5 squared, 25 equals 45. So, oh, hang on. We've missed something, haven't we? Bad, Mr. Moss. Where's the thingamajig? Because that's just the y squared, and if I make this mistake, it's possible you could make it as well. Don't forget this thing, plus y squared equals 45. So now we've got to get rid of the denominator. We've got to times everything by 4 for 25. So 9y squared plus 126y plus 441 plus 25y squared equals 1,125. Ugh, that's not pleasant, is it? Okay, so let's rearrange it. So we'll do the y squared first. So 9y squared plus 25y squared is 34y squared. There's only one y term, plus 126y. And then plus 441, take away 1,125 is a calculator job. And my trusty calculator tells me that's minus 684 equals 0, which is double yuck. Are there any factors that go into that? Well, what have you got? 1 and 34. Can you get 34 into 126? No. Can you get, what's the next one? 17 and 2? Well, you can definitely take 2 out of it. Yikes. So you can divide everything by 2, which will give you 14y squared, plus, no it wouldn't, 17y squared, sorry, that's 34 divided by 2. If you divide this by 2, you get 63y, and if you divide that by 2, you get 3, 4, 2 equals 0. And 17 is a prime number, and it certainly doesn't go into 63, does it? No. Does it? 4. Does it go into 342? Yeah, who knows? But it's so horrible. Just jump and use the formula, okay? Whacked into the formula, this gives us y equals 3, or y equals minus 6.7 to 1 decimal place. And then our x values, if we sub those in, give us, what do we get for 3? We get 6. So x is 6. And for this one, we get y equals, so x equals 0.2 to 1 decimal place. So make sure you write them down as the pairs. 6, 3 and 0.2, minus 6.7. And let's have a look at Desmos. Does the graphs agree with what we've done? Well, yes, it does, thankfully. Okay, so there's our 6,3, and then to 1 decimal place, there's our 0.2 and minus 6.7. But as you can see, horrible. So that's why you really, if you can help it, you want to avoid the nasty fractions. But sometimes you have no choice, and then you've just got to be careful. All right? Another example here, x squared plus y squared equals 9. So we know that is a circle, and x minus y equals 5. Well, x and y are both power 1, so we know that's going to be a linear. So linears and circles, 0, 1 or 2 intersections. This was a nice candidate for equalization or substitution, doesn't really matter which. So let's do equalization this time. So we have x squared plus y squared equals 9. So let's change that to x squared equals 9 minus y squared. X equals 5 plus y. So x squared equals 5 plus y squared. Okay, so we've got x squared on the left-hand side, there and there. So that means this and this have to be equal as well. So that's eliminated our x. So 9 minus y squared equals 5 plus y all squared. Multiply everything out. Equals 25 plus 10y plus y squared. Let it equal to 0. So we should have 2y squared. We've taken that across, plus 10y. 25 take away 9 is 25 take away 10 is 15, so it must be 16. 16 equals 0. Coefficients of all three terms are even, so we can divide everything by 2. So y squared plus 5y plus 16, so that's 8 equals 0. So factorising, well, 8 is 1 and 8 or 2 and 4, and they're never going to get to 5, so this patently isn't going to be a factorisable job. So can we use the formula? So let's see. So a equals 1, b equals 5, c equals 8. So we substitute in x equals minus b plus or minus square root of b squared minus 4ac all over 2a. What do we end up with? We end up with equals x equals minus b, so minus 5 plus or minus the square root of, so b squared 5 squared minus brackets 4 times 1 times 8 all over, whoops daisy, 2a, which is 2 times 1. Now, before I calculate anything out, I can see, if I think about it, if I look inside the square root, I've got 5 squared is 25, I'm taking away 4 times 1 times 8, which is 32. That's going to give me a negative inside the square root. And at GCSE Maths, we don't do negative square roots. This means this has no real roots. Now, if you'd have typed this all in and worked it out, you'd have got an error on your calculator, and then you'd have probably thought, oh, I've done something wrong here. But an error on your calculator means that there's, unless you're using the complex numbers function, that you've tried to square root a negative usually. So there is a method that means you cannot do this. Okay, now if you remember, inside this formula is this b squared minus 4ac. Now b squared minus 4ac is called the discriminant because it discriminates the number of roots you're going to get, number of solutions. Okay, and you should be able to see here that if b squared minus 4ac is greater than 0, you'll get 2 solutions. And the reason you get 2 solutions is because if it's greater than 0, you can have a square root of it, and then you're adding and subtracting that square root, so that will give you your 2 solutions. If b squared minus 4ac equaled 0, you'd have 1 root or 1 solution, because if it equals 0, the square root of 0 is 0, and if you're adding and subtracting 0 for your 2 solutions, you're going to get the same value. And if b squared minus 4ac is less than 0, you're going to have no roots. Now, it's not that you're having no roots, they're called no real roots, okay, because there's no real numbers generated, okay? And that's where there are no intersections, and that's what we have here. So just be careful of that, okay? So this is a situation where we've worked out that there are no real roots, so there's no intersections. Let's check with our old friend Desmos. Where is it? Here we go. And as we can see, the line doesn't intersect. So we've proved algebraically what we've proved by looking at a graph as well. Now, if you got only one solution, then that would be a tangent, okay? Because you'd actually be getting two solutions, they'd just be the same solution, all right? So sometimes, if the question says, can you show that this line is a tangent, or is this line a tangent to a circle or to a curve, instead of having to go through the whole palaver of working out what the solutions are, you can use the discriminant to find out, okay? And sometimes that'll save you quite a bit of time. So that's it, really. That's a long overview through and some examples of linear and quadratic, or linear and cyclical, or linear and reciprocal simultaneous equations. But as you can see, the method itself, even though the questions are quite different, is a simple method. It's just a lot of steps, and it's very easy to make mistakes. So just be careful and think about what's going on. And if you aren't doing it in an exam condition and have access to Desmos, do use it as well to check what's going on. Okay? Bye-bye.